Sean's reputation is preceding him, so everybody knows he's a great speaker. Have a few announcements, but I want to give an opportunity for people if they have an announcement that they want to make. Anybody have anything that they need to share or want to share? Okay, so one thing I want to say is that if you've been going to the meetup, there's a new feature of meetup that we've opted into. It's called WePay, and it allows people to kick in a few dollars to go to the cost of running the meetup, because meetup, of course, is absolutely free to attendees, but we pay a fee to have the meetup itself. And so if you go to WePay, you can just kick in, and there's very small amounts. I don't know what exactly. I think you can use like $1 or $2. If everybody does that, then we'll recoup all of our costs. The other announcement I want to make is that today we opened registration on C++ Now, which is a conference that will be in May in Aspen. And I think it's a really exciting and really fun conference. We've got a few people here who've attended. In fact, I guess we have 2 people here who've been keynotes at that conference. So we're really excited about that. What I would tell you is that registrations tend to go pretty fast. We opened today, and we already have 20 registrations. And there's only room for the entire conference is only 150 people, of which speakers are usually 50 or 60 of that. So we don't have very many open spaces. So if you're interested in going, and I really encourage you to, it's a great experience, I would encourage you to register very, very soon. Okay, did I miss? Yeah.
And that doesn't apply to people who have submitted proposals.
If you have submitted a proposal, then we're holding a spot for you. Don't register until you are contacted by the registrar, who will have special instructions for you. Yeah?
Can you just contrast what CPP Now is compared to like CPPCon? Like I've seen many of the videos of CPPCon, so what differences are there?
Well, so to start out with, there's a lot of overlap, right? You'll have some of the same speakers, you have a lot of the same attendees. However, the focus is a little bit different. C++ Now is kind of more for library developers. It's kind of a really cutting edge stuff. It's a smaller conference and really intense. CPPCon is more mainstream. It's going to be a larger conference. There's going to be, instead of 3 tracks, there's 6 tracks. There's a lot more content. But there is an awful lot of overlap in terms of both the content, the presenters, and the attendees. So it's kind of where you want to go. I think that C++ Now is a more intimate kind of setting. It's smaller. There's a lot more participation with the audience, and sometimes sometimes the talk takes on a whole characteristic of going back and forth with the audience. That's much less likely to be in CPPCon, where the audience is larger and kind of more give and less give and take. Does that seem fair? I mean, who's been to both? Richard, would you say, was I characterizing them fairly?
I would say C++ Now is very cutting edge, discussing what's happening. C++ Con, very informative, and both are excellent.
Okay. So I guess I should say there's one other announcement. After our meetings here, we will go to Tide House here in Mountain View, and we always invite the speaker, but Sean can't make it tonight, so we're going to talk about him behind his back. Yeah. So if you really like to talk, join us and we can talk about it. If you really hate to talk, join us and we'll crash it. Either way, join us and have fun. And the other thing I should say is we have this meeting, which is a formal meeting. You see the format. We'll do this every month, the second Wednesday of the month. And then on the fourth Wednesday of the month, we also have a meeting, but it's a different sort of thing. It's a much smaller group. It's sitting around a table. We do lightning talks. There's more Q&A. It's much more informal, and it's at a different location. So if you go to the meetup, you'll get information about that talk. But we have 2 meetings a month. And yes, sir.
And since you won't plug your own talk, I should also say if anyone's in San Francisco next Wednesday, John Culp himself is giving a talk on R-value references, move semantics, and perfect forwarding, and in general, Chapter 5 of Scott Meyer's Effective Modern C++. That's in San Francisco at Mixed Panel, also announced on the meetup, so you all probably know about it already. But he's not going to say it, so I should say it.
Thank you very much. All right, yes.
I have one. So the D programmers have their own meetup now, and our first meeting will be next week on the 22nd, somewhere in Sunnyvale. Find it on meetup.com, please.
That's Thursday?
Is it Thursday? Yes.
Thursday night.
22nd, and Andrei Alexandrescu here will give a speech on, of course, a topic on D.
Also known as the language that cannot be spoken. All right. Thank you very much. I'm going to turn you over to Sean, who's going to talk to us about concurrency tonight. Thank you very much.
So, how many people have seen one of my talks before? Fair number. How many people have not seen one of my talks before? You're all good, so it's about 50-50. I'm going to apologize in advance for this talk. I think it's going to be a good talk, just not tonight. What I mean by that, I got invited to give a talk in Moscow at a C++ users group in February, and somehow I ended up with a 2-hour keynote at that. And so I'm trying to prepare a very long talk for that. So when I got invited to do this, I thought this would be a good trial run. I wanted to kind of cram it down to an hour, and the talk isn't quite done. So I've got the beginning, and I've got the end, and I'm going to wave my hands a little bit in the middle. There's enough there, I think you can all follow along. A little background on me. I work at Adobe. I've been there roughly 20 years, minus a 1-year sabbatical I took at Google. I work on products these days. I have for most of my career at Adobe. I spent a while running a research team, but for the last 5 or so years, I've been kind of back in the product space. Specifically, I've been working on mobile products for digital imaging. My title is something like Architect for Mobile Digital Imaging Products. And so I've worked on Lightroom Mobile and a product called Rebel, and then we have a photography SDK that's part of things like 500 Pix and SmugMug. So apps delivered through the App Store. So I thought, as part of giving a little background, I would show just a glimpse of a product called Rebel. This one's been in the market for a while. It's kind of the first product I worked on after returning to Adobe from Google. It's an image organizer and editing app, and it syncs across all of your devices. And many of the features of it are now part of the Lightroom mobile ecosystem if you're a Lightroom user. So it's running the same imaging engine that's the professional imaging engine from the desktop Lightroom. Some things to point out here. These are all images that are stored on the web, and these are streaming through my phone. Okay, so we're just flipping through, and there's a huge number here. So you'll see it fill in gray, and then populate fairly quickly, filling in the photos. I flip to one of the albums here. This image is a 47 megapixel image off the Leica S2. And we can zoom in. I don't know if you can see the hair there on her sweater. Right, we can see every last pixel on this image. Pan around. We can edit it live on the device. Okay. Now, first time I brought up this app, it was on an iPad 1. Didn't perform quite this well, but pretty close. This is on a Retina Mini, so a little more horsepower under the hood. But this device isn't nearly fast enough to keep up, especially in the editing space. Okay, so when I slide the slider here, it's an illusion that we're getting something close to 30 to 60 frames a second. Okay, it's actually only capable of rendering at full quality, maybe 3 to 4 frames a second. So what's going on is in the background is doing incremental rendering and it's filling that in. And when I edit and I'm zoomed in, I'm not editing the entire photo, I'm only editing what you're looking at. And I'm rendering all the rest of the pixels live as you're panning around. Okay? And pulling off the illusion that this is a fully updated 50 megapixel image. Okay? So that's the kind of stuff that I do for Adobe, is how do I take our technology and make it fast and put it on mobile devices and pull off this illusion that it's just all fluid and smooth. I had a good friend tell me the other day that I work in a space that's this odd intersection where machines are never fast enough, we never have enough memory, and yet users expect a completely fluid user experience. So I thought that would be a little bit of a good demo, kind of set up a talk on concurrency. Right. Now, I gave a talk at the Going Data Conference, which is now CPPCon, about a year and a half ago. I missed CPPCon this year. And the talk is called C++ Seasoning, and it was by far, I think, the most popular talk I've ever given. It's close to 100,000 views on YouTube now. And a bunch of people asked me after that talk to write a book based on the content. So I've been slowly working on a book every time I get invited to give a talk. The title of the book is Better Code, and this is kind of where we are. We're up to concurrency. I've given a talk on regular types, implementing complete and efficient types at, what conference was it? It was at C++ Now last year. Algorithms are part of the seasoning talk, as is a little bit of concurrency and runtime polymorphism with no raw pointers. I haven't done the talk on the data structure aspect here yet, and you guys are about to see the start of the concurrency talk. Each chapter of the book has a goal. And the goal for concurrency is no raw synchronization primitives. Okay? So don't use them in your code. What I don't mean is don't ever use them. Okay? What I mean is use them to package up a facility in a little standalone piece that's basically just that mechanism, right? All packaged up, that the rest of your code can use. Don't be sprinkling mutexes all over the place in your code. Don't be sprinkling atomics all over the place in your code. This is a common themes in the book as I evolve it here. Manage relationships, and what I mean by that is we want to be able to reason about code locally, right? So we want to minimize the connections from code all over the place. I believe it's very important to understand the fundamentals of how things are put together. And my very first talk on this, the start of the book here, it starts with how do transistors work? Right? So I really think it's important in order to understand how to use mechanisms that you understand how they're built. And then try to write your code simply and evolve it. So concurrency. Distinguish between concurrency and parallelism. Right? These are the definitions that you'll find in most CS texts these days. Concurrency is when tasks start running complete in overlapping time periods, but it doesn't necessarily mean that they're running in parallel, meaning executing at exactly the same time. I can have concurrency on a single core by time slicing it. Parallelism is when two things are executing simultaneously. Why we want concurrency is for two reasons. One is through concurrency that enables parallelism. Let's utilize more of the machine. Okay. But it also improves our interactivity. Okay. saw my demo at the beginning, I want user events coming in and being able to do stuff, and at the same time, I'm doing rendering in the background and feeding that information back to the user task. Okay. Improving interactivity frequently has an overall negative performance impact on the entire system. Because you need more complicated data structures, you have to slice things up into smaller tasks. I worked on Photoshop for a number of years. It's really easy to make Photoshop run about, I don't know, it used to be about 2 times faster, maybe now it's like 20% faster. And all you have to do is increase the granularity size for how much data it churns through at a time. The problem with that is that's also your tick mark for user interaction. So all of your user controls start stuttering, and your paintbrushes stutter, and you can't use the app anymore. Now, desktop hardware has changed a lot in the last few years, and I don't think a lot of people realize quite how much. If you look at a typical desktop machine, this is how many gigaflops are trapped in your GPU. This is your vectorization intrinsics. That's your multi-core, and that's 1 core. Okay, it's like 0.25% of the performance of the machine. Okay, so if you're just writing code, the straight line code that's just executing on 1 core, you're leaving 99.75% or so of your machine sitting idle. So my goal is always to figure out, how do I light this whole path up? And the starting point for that is getting to multi-cores. Threads and tasks. There's a fair amount of confusion around these topics too. A thread is an execution environment that consists of a stack, processor state, and running in parallel, possibly time sliced, with other threads. Okay. A task is a unit of work, often just a function call, that can be executed on a thread. Right? So tasks are frequently executed in a thread pool to optimize machine utilization. Switching between threads for processors is a bit expensive. Now, C++14 has some task primitives. It's got futures, which we'll see later in the talk, are a useful construct. And it's got threads, but it doesn't have a thread pool or a tasking system, right? So you keep spinning up threads. It's not particularly efficient. Performance in a threaded system is surprisingly difficult to achieve. Now, this is a horrible graph. Everybody uses this graph. This is Amdahl's law. And this is the graph you'll find on Wikipedia for Amdahl's law, which is why I think it gets pasted into everybody's talks. The problem with this graph is the number of processors are on a logarithmic scale at the bottom of this graph. Okay? And I think that makes it very deceptive as to what the actual performance implications are. What we've got is your speed up the left side there, okay? And that's on a linear scale, right? So what we're saying here is if 95% of our code is running in parallel and only 5% of it is running serialized, then it really doesn't matter how many cores we are, we're never going to get more than a 20 times speed up, right? Because that 5% is stuck serialized. And this goes all the way out to 65,000 cores on the right. Now the problem with this graph is if you drew the line for a linear speed up, it would start at the same origin here, and it would arc up, and it would go through the top of the graph right between about 16 and 32, right where 20 would land there. And at this scale, I would guess the top right corner of this graph is about 4 miles up. Okay? for this graph. This is a zoom in of the origin of Amdahl's law on a linear scale. And this is what I think most engineers these days, at least currently, need to worry about. Unless maybe you're working on superscalar architectures or very high performance computing. We just went up to 16 processors on the bottom, 16 times speed up on the top. The red line is linear scaling. Each one of those subsequent lines is what happens if you just have 10% more serialization. Okay? So if you just have 10% serialization at 16 cores, you're only going to get a speed up a little more than, where is that? It's a little more than 6x. Okay. You're not even going to make half the performance on the machine. Okay. This is what kills you. So, what causes you to slow down? What causes you to fall in Amdahl's law? I stole this from Hartmut Kaiser. He uses this in many of his talks. It's starvation, latency, overhead, and waiting. Right? It's contention. If you read it down, it's slow, so it's pretty easy to remember. Okay? So starvation is we don't want any core sitting idle. We want to keep them fed. Latency is how long it takes us to get a result for something. Overhead is anytime we're dealing with multiple threads, we're incurring additional overhead for how we set things up, how we tear things down. And waiting is if we're stuck on lock contention. I see a lot of confusion with people about thinking that lock-free code is wait-free code. If you look at most lock-free code, it will spin instead of actually acquiring a lock. It can be more efficient, often is, okay, but it's not wait-free. Just accessing shared memory is going to cause some amount of synchronization on your machine and take you down a notch on Amdahl's law. Okay. This is the view that, at least in my experience, most engineers have of writing threaded code. Okay. They say, I'm going to write some object, and I need this object to be thread safe because I want a bunch of threads banging on the same object. And so I'll stick a mutex on it, and one thread can access it at a time, and we'll rotate things around like that for the next guy. Don't do that. That's death. Right? No stops. So, if you can on your machine, use a tasking system. There's a lot of them available. On Windows, you've got Windows Thread Pools and PPL. It's heavily tuned, quite efficient. Apple's got Grand Central Dispatch, which is open source. So there's libdispatch, so you can get libdispatch running on Linux and Android. Runs on iOS and Mac, part of the operating system. Intel has QBB, which is also open source, although not ported to as many processors as I'd like to see it. HPX is another library out of Stella Group, and available on many platforms, especially if you're looking at large-scale machines. Okay. So I am maybe working on a project right now that I can't talk about, unfortunately, where I can't use any of those. So I thought, well, how hard could it be to write a tasking system, right? We can whip one of these out. So let's do that. Well, if you Google online, a full reference, you can't read it at the scale in the corner. But this is a design. It's my image, but the design basically comes out of the multi-programming user guide on Oracle's website. How do you create thread pools and create a tasking system? And what they say is, well, what you need is a queue, and you're going to queue tasks into the queue, and then you're going to have threads who are going to wait for tasks to show up, and you're going to pop them out and execute them. So let's write one. Okay. We're going to use a lock a couple times in here, so I'm just going to do a type def for that. Right. To keep it very simple here. we need the queue part of this, so that's what we're going to write first. Okay. So here's a notification queue. We're going to use a deck. Everybody know what a deck is? C++. Anybody not know what a deck is? Yeah, so deck stands for doubly ended queue, right? So similar to a vector, but in constant time you can push and pop from either end. Not in and of itself a thread-safe data structure, which is why we've got a mutex, so we're going to stick around it. And then we're going to use a condition variable. Okay? I'll explain more about what a condition variable does in a minute. So here's what it's going to look like to pop something off of the queue. So imagine for a minute we have something in that queue. Okay? We're going to acquire a lock, and then as long as the queue is empty, we're going to wait on that condition variable. Okay? So that's going to park this thread. Right? It's going to tell the OS this thread isn't getting used, its queue is empty. Okay? It's going to sit there. So if something wakes it up from that wait, it will check again to see is the queue empty or not. If it is, if it's still empty, it'll go back to sleep. Hopefully, eventually, something ends up in the queue. We're able to move out the front guy from the queue, pop the front off the data structure. Here's what the push looks like. Pretty simple. Got to acquire the lock. We have multiple threads hanging on this queue at the same time. We're going to push back, endpoints back, our function. That's what f is going to be. It's going to be a function here, and it can be a function object, so we can have state. And then on our condition variable, we call notify1. There's basically wait, notify1, notify all, the calls you need to be concerned with on the condition variable. What notify1 does is it says, one guy who's waiting on this gets woken up. If nobody's waiting on it, it doesn't do anything. One guy's waiting on it. You got to wake up. Now, the thing that you're checking in that while loop, if you notice the wait takes a lock, the thing that you're checking in that while loop, okay, waking up on the condition variable, has to be changed with the lock acquired. So even if I had a separate concurrent queue, okay, before I can do notify one, I need to acquire that lock and release it, or I'm going to introduce a race condition. Okay, so that's it for a queue. So now we're going to build a little tasking system. Okay. So we're going to ask the hardware. This is all C++ 11, some of it might be 14 code. So we're going to ask the hardware, how much concurrency do you have? Okay, we'll store that away in count. We're going to get a vector of threads, because we need threads for a thread pool, and our notification queue. That's all we need. And then this is our run loop that we're going to execute on each thread. And basically what we're going to do is we're going to create an std function. It's just void of void. We're going to pop a function off, and we're going to call it. Okay, and that pop might wait to park that thread if the queue's empty. Okay. So we'll initialize our task system. This is just putting one thread in the thread pool for each piece of hardware we have and initializing it with our run function. When we destruct, we're going to join all of our threads. Okay, now we've got a problem here. This is just going to hang the machine because our run loop never exits. Okay, we'll fix that in a minute, but that's going to hang the machine. And then to execute something asynchronously, all we have to do is push it on the queue. Okay, so except for the fact that when you quit, this is a functioning little tasking system. Okay, so let's fix the quit issue. To do that, we're going to go back to our notification queue, and we're going to add one more flag, which is done, just a bool. We're going to add a function, okay, that acquires a lock, sets done to true, and then notifies anything waiting on that condition variable to wake up. And then we're going to change our pop here to return a bool And basically what it's going to say is, well, we're not empty and not done, wait. Okay. If we wake up and we're empty, okay, then we're going to return false. Okay. So, because that means we're done. But we don't want to say if we're done, return false, because we don't want to, we're not done until queue's empty. Okay. Otherwise, we'll return true. And that's it. That's the whole thing. That will now start up, execute, do its job nice and clean. So how does it perform? Really bad. Really horribly bad. Okay? I do not know how many servers are running this code, given that it's on Oracle's website as the way to do it. This is horrible.
Sean,
Yeah?
that's for the competition.
That's for the competition, exactly. Probably not what they're doing on their servers. Okay. Okay, this is horrible. Now the benchmark on my little speedometer here is max over there is what Apple's GCD does. Okay, under a heavy load, right? And this is about 1/10 the speed of Apple's GCD. Okay. Why? Anybody have a guess?
Contending for one lock.
Contending for one lock, right? Right. Good. Most of the time people answer to that, you got a bad queue, right? You're using the deck, decks are overweight, okay? We can go into this and mock out the deck entirely and replace it with a count, where push is increment the count and pop is decrement the count, right? As if it's just an int, right? Nothing could be faster, and this code won't speed up at all, okay? It's not the queue, it's the lock. We created something that's exactly this, right? We've got one queue, this one object, and a bunch of threads banging on it, and only one can go at a time, and everything is serialized, and our performance sucks. Okay, it's totally thread safe, right? It doesn't crash. It just sucks.
I have a question.
Yep.
When we say performance sucks, other than the pops that you were showing, does it have an impact on CPU utilization?
So it does. It has a huge impact on CPU
So is it
utilization.
high or low?
CPU utilization is going to be very low. So if you run this under a heavy load where you have lots of tasks getting queued and relatively small tasks, you will have a really hard time getting your overall CPU utilization above maybe 3 to 5%. Okay. So how should we do it? Okay. Here's what you want for a tasking system, right? You want to put a queue per thread, okay, in some kind of scheduler that doles things out to threads, okay? So now things aren't fighting with each other anymore. That's a better design. So let's do that. We'll replace our one notification queue with a vector of notification queues, okay? And we just need as many of them as we have hardware concurrency, which is as many threads as we're going to have. Okay. And then what we're going to do is in our pop function here, we're going to pop, right, I, which gets passed into the run, is the index for this thread, okay? So I that's getting passed in is the index for the thread, so we're going to pop off our own queue. Okay? And then when we clean up, instead of notifying one queue that we're done, we're going to notify all the queues that we're done. And then down here, when we push, we have an atomic index that we're going to keep incrementing, okay? And we're going to mod it with the count of the number of queues we have to get an index there for a vector, and that's what queue we're going to push onto. Okay? And we only need to increment our index once there. What do people think? How's this pedometer going to go? What's that? It'll be better. How much better?
Twice.
Twice?
3 times.
3 times?
Go back, I didn't look at how
More.
many can you do that? Go back for a second.
What's that?
One question wasn't how many cores,
Any questions on there?
It will vary, actually.
It does depend on your
Yeah.
concurrency, right, or how many threads you have.
What's that?
It does depend on how many cores you have.
Oh, certainly, it does depend on how many cores you have. So, for my testing, I was running on 8 core this machine actually. So, not 8 real cores, but 8 virtual cores.
No, it'll be
Are
more
the
than
tasks
4.
here
It'll be
More than twice. Yeah.
the tasks, they are uniform?
My tasks were relatively uniform and all fairly small. So, let's see. So, in heavy load.
See, my guess is index is atomic, you still gotta synchronize an index, right?
Yeah, we still have to synchronize on index, although it's not that bad. We're only incrementing the push here. Let's see. Yeah, there's that. Okay. Here's our test. Quite a bit better. Okay. Okay, so now we're only about half the speed of GCD. Okay. So what do they do that's different?
Do you have a GCD code for reference? What you're doing for using GCD?
So, the actual calling it?
Yeah.
I'll have to put that together in some readable form with Jeff. Okay. So it's basically just queuing a bunch of function objects to GCD and say execute them. So doing the same on both, and it's like testing it with 100,000 objects, so I can kind of filter out the noise. So here's the next thing. We want to insert this slice in the middle, which is task stealing. How many people have heard the term task stealing? How many people think it's this horribly complicated thing? A couple people. Yeah. Yeah. So it's not as complicated as you would think. The idea is pretty simple, right? Which is to say when my thread wakes up here and it grabs something from the queue, okay, it can take something from its own queue, and if its queue is empty or busy, it'll go and grab something from another queue. Okay? And there's a lot of complicated ways that you could set this up, and there's task stealing mechanisms and there's task requesting mechanisms. So I wanted to write just a dead simple task stealing system. Now this task stealing has another advantage, which is if you have tasks that are running that are variable length, and so one of your queues is tied up for a long time, as the other things become available, they'll steal tasks from the thread that's busy, right, and it will balance your load. Okay, so task stealing has two advantages. It's going to speed us up, just in general, because we're not spending so much time waiting, okay, and it's going to balance our load. Okay. So we're going to go back to our notification queue, and we're going to add 2 new functions, and they're relatively simple. One is a try pop function. Okay? And what this is going to do is it's going to try to acquire the lock, right? And if we don't get the lock, okay, or we're empty, then we just return false. Otherwise, we do the pop. Okay? So we don't wait, right? We just try. If the lock's under contention, just return false. Didn't get it. Okay? And we'll add a try push too. Okay? So we can improve our scheduler in the same way that we're going to add a task stealing system. So when we try to push, it doesn't really matter what queue we put it on, right? So if one queue is under contention, try the next one. So that's the basic idea. Okay, so if no lock on our push, we just return false. Okay, so now we need to fix up our run loop here. So what are we going to do? Before we wait on a pop, we're going to run around all the cores, and we're going to try to pop. Okay? So you want to run around all the cores at least once. Okay? Now, there's a lot of playing that you can do to tune this, right? Is once enough? Should you spin for some number of, for some amount of time around? Right? So you at least want to make one pass. You could make more passes spinning, okay? You could do it for amount of time. You could do it just a fixed number of counts around. We could improve our pop and actually return whether or not we were empty or whether or not we were in contention. So we could only say, well, we'll only fall into the wait if we've determined that everybody's empty, or at least for a brief moment of time they were empty. So there's a lot of things that we could do there, right? But this is the simplest thing. We'll just run around. Okay. Now the same thing here, we'll run around on the push. Okay. Now here on the push, okay, on the pop, eventually you're going to be empty and you have to wait. Okay. But on the push, really, if you wanted to, you could just make that a while loop and just run around, just cycle around until you found something. Okay. In testing, I haven't been able to find that the push side makes any difference. I can tune a lot of performance on the pop side, but the push side doesn't really seem to make much difference. Okay. So I just run around once and then wait on one to push. Yeah. Yeah. Now we're within spitting distance of Apple's GCD, right? And if we tune the pop a little more, right, I can beat them in some cases and lose in others. GCD does a little bit more work than what we're doing. They're balancing across the entire system, and they have support for continuations and other stuff going on.
Doesn't this make the assumption that all queues are equal in priority?
This currently does make the assumption that all queues are equal priority. Okay, so GCD does not. There's two ways that you can get multiple priorities, right? We could add to our notification queue. We could actually make it have 3 queues if we wanted 3 priorities internally. It's probably the easiest way to do. If we wanted kind of a gradient of priorities, we could stick a priority queue, which is typically a heap structure. Those will both perform quite well in here, right? I didn't want to go into detail on that because it's slides in the talk. Yeah.
Did you do any experimentation with lock-free structures at all?
I did do experiments with lock-free structures and queues, and the queue time surprisingly matters nothing. It probably would on, Android devices notoriously have a bad allocator, and so the allocator itself has a single mutex around the allocator. So if you're doing an allocator inside of a mutex, you're locking everybody out. In which case you want something where you've got a pool or a circular queue or something like that. But on this hardware, it doesn't matter at all. I tried heavily tuned concurrent queues. I tried building super lightweight queues and putting them in there. It's in the noise.
Your example didn't have any like core affinity, did it? Did you experiment with that?
Core.
So that one queue is in the local, is in the cache of one particular.
Oh no, I have no core affinity going on or trying to do anything with that. Right? Just the idea is trying to keep everything that's in one queue local, so in memory, right? So you're not thrashing memory between your processors. I make no attempt at that. As a deck, it's going to do a pretty good job because it's blocky data allocator anyways. It's not a linkless data structure. So, but I did try it with linkless, which is probably the worst case, and it didn't matter. Yeah?
So, you have the same number of queues as threads?
Yes.
Have you looked at what's the impact if you don't have the same?
Yeah, so it gets to be problematic. The question was, I have the same number of queues as I have threads, right? If I have more queues, then a single thread has to be waiting on multiple condition variables in order to get woken up, right? So if I have more queues than I have threads, then somebody has to be waiting on multiple things, okay? And that tends to be relatively expensive and no real win from it. And if I have less queues, then I have threads, and then I'm back in the lock contingent case. So the typical design is you have one queue per thread. Okay. So there's other things that you can play with in this, which is you can put in timed, I'll get to that in a second. You can put in timed mutexes in there, and instead of keeping these threads just parked, you can say, if the thing's empty and nobody's woken me up after a while, just kill the thread and free up that resource for the rest of the machine. So that's another optimization. Well, let's go to this person first.
So speaking of allocators, as far as I know, allocators tend to have a global lock. So if that's correct, creating tasks and functions.
Yeah, actually,
is that
I mean,
pressure on?
most platforms not. I mean, iOS, like I said, Android is somewhat an exception, but iOS, Mac, Linux, Windows, any recent version now has a fairly efficient memory allocator, right? Where to both do an allocation or free, it doesn't have to go to a global lock. You know, 5 to 10 years ago, that was a huge problem, in which case I'd say, like, take Intel has their own memory allocator that they make available, and there's a half a dozen of them around, in which case I'd say use a different allocator, which opens up a whole other set of worms if you're trying to bring up a different allocator inside of an app. But that would have been the answer. Question here?
So if you look from the outside of that task system, when you're trying to feed it multiple tasks, you have the context of breaking up the image into, let's say, tiles. Have you looked at processor prefetch versus horizontal versus vertical tiling, making tiles more vertical or horizontal for speeding things up?
Yeah, so the question was specifically about kind of image processing, where we're dealing with images. We tend to break images up into tiles that we process a piece at a time. And have we looked at, is it better to have tiles that are, you know, wide and squatty, or tall and skinny, or we actually have done a lot of looking at this. The answer always comes back that square's best, which is somewhat surprising. If you're just trying to rip through the entire image, then wider does better, right? You basically want to do everything kind of scanline oriented and rip through memory really fast. So if I were to write an application that I just wanted to feed in an image and have it grind through that whole image super fast, that would be best. But the trade-off is if I'm looking at a view inside of a window, then if I have a wider thing, I have more pixels outside of my view that I'm dealing with at any point in time. Okay? And so I'm making a negative trade-off for that, right? So yeah, we've done lots of analysis, and the answer always comes back to be about square, so we just make them square. So, question here.
So, is there any impact on having more number of threads and the number of cores? Is there any correlation with number of cores?
Right, so the question was, is it better to have more threads than you have cores? It depends on what you're putting into your tasks. So the one time you have an advantage of having more threads than you have cores is if you're doing blocking I/O on something. Okay, so talking about how to do efficient I/O efficiently is a whole other talk.
Because OS also does this time slicing. So
right, it will do time slicing, but the time slicing is relatively expensive, right? Going through a kernel switch on threads is quite expensive. But that also varies a lot by OS, and so it's always worth checking, right? So yeah, usually you want kind of one-to-one. Sometimes you actually want to purposefully underutilize the machine if you know that you have some other subsystem in the machine that is chewing up resources, right? So like I said, I like writing code like this code, which is very short and sweet, because I can bring it up on a machine very quickly. It only requires C++11. I can run it inside of a console. I can instrument the heck out of it, and I can play with all the sliders and figure out what's going to look best. And I frequently recommend people, everything you write, try to write it independently, run it in isolation. It makes testing a whole lot easier, for one thing, but it also lets you experiment with it and tune out the performance. So I wanted to talk a bit about features, right? And this is where I have to apologize, because this is where we end up with a hole in the talk. How many people here know what a feature is? How many people do not know what a feature is? Okay, a few people. Okay, so the idea with the feature, these are in C++11 and C++14, is that if we take some function, right, which could be a function with state, a function object, okay, and what we want to do is separate the function from the result. Okay, we want to split those two apart. The result we call a future, right? It's not actually the value. It's, can't use the word promise because a promise is the other end in these systems for some weird reason, but it's an IOU. Okay, so a future is an IOU for the result. Okay, and the function that we split off is something called a packaged task, which is intended to be executed exactly once. Okay, so it will execute once somewhere else. We can throw that, since it has no results now, if we bind some arguments into it, we can throw that into our tasking system and execute it asynchronously. And somehow magically, the answer from that will end up in our result, which is getting held from some other piece of code. What futures allow us to do is write code that looks like it's straight line code, right? I can say a future for this double is equal to asynchronously calculate, I don't know, asynchronously determine if this huge number is prime or not. Okay? Okay. And that goes off asynchronously, and I'm holding on to this future, which is a token for the answer. Okay? So so minimal code transformations, your code looks like it's basically straight lines, but now instead of actually holding values, you're holding futures for values. Okay. Now C++14 has futures, and they do a few things very nicely. They do something called exception marshalling, which is to say, if the function that's executing over there somewhere throws an exception, then when I go to get the value out of my future, the exception will throw out my future. Okay, so it'll disappear over here, reappear over there. Right? So the other thing it does is something called sever notification, which is called a broken promise. Right? The sending end of a future is called a promise. I always thought it was backwards. But the sending end is called a promise. And so if your function goes away, destructs, without getting called, okay, then it sends an exception that's a broken promise, so that the receiver, when they go to get it, they don't wait forever, right? They immediately get an exception that says, hey, that's a broken promise. There's no value ever coming on this channel. Okay? But C++14 futures lack a whole bunch of stuff that's very necessary. Okay? The title of the slide, what year is this? Came about because I was sitting in my office working on yet another tasking system, and a colleague of mine, Mark Hamburg, who's very well known for his work on Photoshop, dropped in to visit. He lives up in Seattle these days, and he said, I'm working on a tasking system. He happens to be writing his in Lua, and I'm like, I'm writing one too. It's like, why doesn't anybody get this right? Okay? Some people have some of these features, but you're going to see there's a ... There's a whole bunch more stuff I want out of the system, right? Right? And I'm going to end up writing it myself. Again. So, continuations. So, I have this future right now in C++11. The only way to get a value out of the future is to call this function on it called .get. The problem with .get is it's a big stop. Okay? You're stuck waiting until the asynchronous thing comes back. Okay? So what you want to be able to do is have .then, which is to say hand this future a function which takes the result of the future and will execute when that thing is available. Okay. So then you want a notion of joins, which is you want to be able to say when all of these values are available, then execute a function with the results of all of those values. Okay? I want cancellation. Now, some tasking systems have a form of cancellation. PPL has task cancellation. Intel TVB has cancellation. Okay. What I mean by cancellation is not that I can take some task that's currently executing and halt it mid-flight and leave my machine in some unknown state. What I mean by cancellation is if I let go of the last future, okay, right? I had some function, I packaged it up, I got a future from it, maybe passed that future around in my code. When the last of those futures goes away, if that task hasn't even started yet, then it should never start. Okay? That's what I mean by cancellation. And when you look, when I'm doing things like scrolling through a bunch of images, what's happening? I'm issuing a bunch of asynchronous requests to say, go fetch those images, right? And then they scroll off the top. And I'm like, oh, never mind. I don't want that anymore. Okay? When I'm doing rendering and you're sliding the slider around and I'm trying to keep up at 60 frames a second, if you slow down, I'm going to try to render a full resolution version of that image, and if you move the slider again, I'm going to be like, oh, never mind, I don't need that. I need something fast and small. Okay? So I want cancellation. And then something that most apps run into is at some point you want progress monitoring, which is given a future, I want to be able to ask it, what % done are you? Right? And since a future can be associated with a task and I have continuations, which means I can then do this, give me another future, then do that, give me another thing. When all of these things are ready, do that. I want my progress tracking to track through that whole graph. Okay. And C++ futures don't compose, at least not easily, to add these features after the fact. Okay. So blocking on STB future get has two big problems. One is that thread resource is just consumed, it's stopped. Okay. And then the subsequent non-dependent calculation on that task is also blocked. Right? So you're just stopping the world. So we already talked, other systems tend to have some form of continuation. So this is what we want, right? We've got our function, which returns a future, and then we want to say when that future is available, call another function, giving me another future. Right? And I want to be able to do this. Call a function, give me a future. When that future is available, do this function and do that function, give me two new futures. Okay? So then I want if the last copy of the future is destructed, then it cancels or no ops out the task and releases the resources held. And that's important too. Right? If I cancel something and it's hanging onto a 50 megapixel image, I want that memory back. Okay. So how are we going to build something like that? What we're going to do is our package task and our future are going to have shared state. Okay? And the hard line there is going to be a shared pointer, right? A ref temp pointer. And the dotted line is a weak pointer. How many people know what a weak pointer is? Everybody, good. People use too many pointers. Right? So if I take this thing, right, and I'm only holding on to the futures on the ends there, right? Then that has to turn into this construct. Okay? I've got this task, which is holding on to a shared state, which has its two continuations, right? It needs to call two things when it's done. Okay? So those are going to be the, right? So those little circles are just like big circles. Okay? So those have those shared states. Those shared states have to have a strong reference for the argument. They're hanging on to the future that they're going to execute on. Okay? And then my final two futures up there. So if you look, all the arrows going to the left are strong pointers, and all the arrows going to the right are weak pointers. And so if I let go of an end, then my graph unravels. Okay. The next piece, and I would show code, but this is where there's a hole in my talk for that last. But imagine I showed you code on how to write such a thing. You're just going to have to imagine. So the next piece you want is a join going this way, right? Instead of fanning out, we want to be able to fan in. Okay? So we want to be able to say when we have two futures, go and execute that. And this is the big hole in my top. So I will tell you briefly about how that's going to work, right? What I don't want to do is have those two things waiting, even on a condition variable, for the tasks that feed into them to complete. Okay? What I'm going to do is I'm going to attach a continuation to both of those guys. And so when the first one finishes, it will call that continuation, and it will just decrement a little atomic in my task over there that says, I got called one time. I got two arguments, but I got called one time. And when the second one executes, it's going to call that atomic again. Say, I got called twice. I have two arguments. I was called twice. I should call the next thing in the chain. Okay? So nothing ever has to wait here, right? So I can build this join out of the same continuation mechanism. Okay. Now we're going to kind of turn a page here, right? This would be the next chapter in the book, and you guys get to get a glimpse of it. Something called property models. Okay. So we've got futures, we've got tasks. Does everybody kind of have a general notion of what we're talking about here? Okay. Yep.
So in the previous slide, so for every time it goes from left to right,
yep,
which is stop, all continuations, is it going to create one shared state for each feature, and next time around?
Yes, each future will have one shared state, and they will kind of be chained from
and all of
continuation.
them will be discarded, right? Because future success.
When the last future goes away, yes, they all get discarded of the chain.
So my question is, next time around, you have to create the new features, some new shared
Yes,
states.
and you're on this slide, so we'll talk to that in a moment. Question over here?
What about cycles?
What about cycles? Well, because everything's kind of value semantics with your futures and stuff, there's no way to attach a future, right? I get a future at the time that I break a task up, so there's no way to attach a future to a task that's already been created.
You can't create promises
without the corresponding future, so you can't build a cycle, okay? Which is a very nice attribute, right? Okay. So to your question over here, exactly this question. We're building this graph, right? People who build these tasking systems, what tends to happen is you build the graph, boom, 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 right? I'm doing, execute this thing asynchronously, give me a future for it, execute this thing asynchronously, give me a future for it. Those are all heap allocations doing shared memory so that we can do the communication. And those functions are all set up to execute exactly one time, and then we tear it all down, and then we loop around and we build it all back up. Okay? That sucks. Don't do that. So what if we persist the graph? Okay? And we kind of hang on to kind of initial values on this end, and now we can set these values, right? Basically feeding arguments into this graph, and it flows through, right? And we can just reuse the same graph. Right? Now, if you did that, okay, so we can allow multiple implications of the task by just setting the source future values, and each change triggers notification all the way down, right? And those things can happen asynchronously. So, and this is what's known as a reactive programming model, right? So many people heard the term reactive programming or functional reactive programming, right? The easiest way to think about it is a spreadsheet, right? I change a value, it goes through a bunch of calculations in response, right? The spreadsheet is holding on to my dependency graph.
Is this the same thing that TBV would call a pipeline or a flow graph?
Yes, so TBV has something called flow graphs that are exactly this. Okay. So, what if we got rid of the arrows? Right? We have a graph, a bunch of things connected. What if we got rid of the arrows? What does that mean? Okay. So, this comes up a surprising amount of time when you're writing a piece of software. If I have something that depends on something else, frequently that relationship is a two-way relationship. Okay? So, if I change this side, I can change that side. If I change this side, I can change that side. Right? It comes up an awful lot when you're dealing with graphics and user interfaces. Right? Right? My canonical example is always resizing an image. Right? I can, if I've got a relationship between the width of an image in pixels, the resolution, and the width of my image in inches. Okay, that's a three-way relationship. I can change any of those two values and calculate the third value. Right? So I can flow through this. When you're doing things like rotating an image and you've got a crop rectangle and the crop has to stay within the image bounds. But I can also grab the crop rectangle and drag that, right? So I can come at it from two ways. That's a three-way relationship, right? Right? If you say things like, oh, I can click on this button to automatically set a bunch of parameters, and that's going to light up this UI control. But then if I change one of those parameters, it needs to unlight that thing. Okay, that's a multi-way relationship. Okay? So these things come up all over the place. So what do? Well, we keep the graph, but we get rid of the arrows. Okay? And what we say is we're going to flow this thing based off the priorities of what were our futures, and then they were our behaviors, and now we're going to call them cells. Okay? So, right, let's say here that A, B, and C represent just a multiplicative relationship. So we can do that by just having a package of functions. So depending on which way we're going to flow through this thing, we're going to execute one of the functions, right? And the rule is, for any given flow, we only execute one function. Okay? So this forms a kind of a constraint system, a particular kind of a constraint system, are called property models. Okay? The flow is determined by the cell priorities. Okay? So each cell gets a priority that determines how you're going to flow this graph, which is usually in response to some external stimulus. Right? So cells, if our values or futures, can only have one in edge. Okay? When I flow my graph, okay, I'm determining the set of arrows. So I've got a rule here that says I've got my value. I can only calculate it along one path. If I'm trying to calculate it along two paths, my system's over-constrained, right? I can't say A is the result of this function and the result of this other function. Okay? Not simultaneously, it's one or the other. Okay? Relationships are functions. We simplify things by saying our functions only have one out edge. Now, we can always then split things. We can always fan out. So I can always say, like, I can always basically return a pair from my relationship and then feed that pair into two additional relationships that peel off the first item and peel off the second item. You know, so I have a function returning a pair, I relate the pair to a function that takes first, and I relate the pair to a function that takes second. Okay? So it's a simplification for reasoning about things, but it's not a limitation. Okay. So that gives me something like this, right? I have this graph that I've got in memory, and I fed inputs from a couple sides, and that determines a flow, and I calculate other outputs. But each of these operations can be asynchronous and can take time. Okay? So they can still be executing concurrently. So what does that look like? top here is at time 1. Okay? I've got the graph. I flowed from my 2 sources. That's the image that we just saw, and I went out to the 2 sinks. Okay? At time 2, I came along and I poked this guy in the middle. Okay? And I set him. And that caused my graph to reflow. Okay? So now my graph has reflowed from that source out to those 2 sinks and over to this sink. But this value is still dependent on those values, which are executing concurrently. So that little pipe that I drew there means that those are one and the same instance of the cell. Okay? So if you look at this, this is one DAG. Okay? It's a graph with 2 flows over time, and it's one DAG. And the place that's grayed out of there is a piece I don't care about anymore because it was overwritten by my sink down here. Okay, so that task has been canceled. Okay, so if you look here, I've got my source flows through up there. This source comes in. I've only got one arrow out of each circle. That's into this square, which is the same as this square, which feeds into that circle. That source feeds into here, into there, into those 2, into those 2. Okay, so what you're going to do here is you're going to create conceptually, you've got a stack of these things going over time. The user's making changes up here. That's reflowing the graph. That's triggering a whole bunch of asynchronous calculations. And it's getting chased along from behind as those things execute. The graph kind of collapses from one end. And as the user changes things so they're like, I don't care about it anymore, pieces get trimmed out of the whole system. Okay? Okay, so I've got it growing this way over time as the user's making changes, from the bottom up as it's completing, with dead sections of the graph being pruned out. Okay? We are already over time. Okay. But a final thought for you is how you want to write systems like this the way we do now. Okay. So if what we're building is heavily asynchronous systems that are graph flows, right? And this is just one particular kind. There are other examples. Okay. Is an imperative language that's building a graph, trying to pull off the illusion that things are executing sequentially, even though they're not, the right answer. If we can hand the graph to the compiler, okay, the graph can determine which tasks can be executed in parallel. Okay. The compiler can determine whether or not our system is flowable given any set of priorities. The compiler can determine whether or not we have cycles that we've introduced into our graph and not enough outlets to solve those cycles. Okay? So just a question, right? The more we build kind of asynchronous, fast, complex systems, and this applies whether or not you're doing it on this device or whether or not you're building systems that are trying to do like what Facebook does, which is connect to some huge number of nodes, the more an imperative-based language starts to creak, right? It starts to feel like an artificial limitation. So that's just the thought I'm going to do it, and then you can debate your heart's content without me at your cabinet here at Tight House. And that's the end of my talk.
I really want to see the code for the last section. So when you said it was a stack, I mean, are those memory allocations? You said before you said that unused nodes collapse, but you want to keep the graph itself, I guess, as a template, perhaps what you were saying, and then you're making copies of that, and those allocations are disappearing over time?
Exactly. So you can think about it as I've got an undirected graph that I keep making a copy of and flowing, okay, and pruning it as it goes, right? So the structure of the graph is the same at each level, but the flow is different.
So
And also your original timing. Did you compare any other type erasure mechanism besides standard function, such as package task or even virtual base class?
I did a little bit, and especially with GCD, because it doesn't take like an STD function. It effectively made no difference, but the functions that I were trying would have fit in any small optimization for an STD function. But if they wouldn't fit, then you'd probably be in a heap allocation, you know, even if you were doing a void star and a function pointer. So, yes.
In Boost 150, something around that time, I saw continuation popping up, and it's just the line. I was just looking by, I saw like then and when are popping up. How well does that perform? Is it worth looking into the Boost continuation stuff for the futures?
Yeah, I haven't timed Boost futures. I do use them. They probably perform better than the code I would have shown you if I had gotten the code in the slides. So I've only glanced at the code, but I haven't profiled them. So, but yes, I think they are worth using. And that's certainly the direction that the standard's going. I mean, that's where it's coming from, right? We should be getting, within the standard, we should be getting then continuations and win all. Unfortunately, I don't see cancellation appearing in the standard, and if it does appear in the standard, it will probably be as a separate external mechanism, much like it is in PPL, which is quite a bit more difficult to kind of wrap into a future, right? So unfortunately, these things just, nobody's figured out how to make these little building blocks compose well, including me. Yeah.
What is it about OpenMP or threading building blocks or any of the other libraries you mentioned that would make you not want to use them for a task system like this?
I would use any of them. So the particular reason is that right now I'm working on a platform. Why I said I have to write a task system? Well, there's two reasons why I said I have to write a task system. I'm working on a platform right now where it's not on a processor for which any of those codes are ported. Okay, those libraries are currently ported, or in case of a couple libraries, there's licensing restrictions that won't let me use it. Or things like libdispatch has a reliance on libkern, and the platform I'm on doesn't have libkern, which is your libkernel. So I decided to sit down and just write my own to bring this up. You know, eventually I'll probably replace it with something else. The other reason why I write things like this is to understand them. So I'm somebody who I tend not to try to use something until I feel like I understand how it works and what the ins and outs are. And a good way to do that is usually, how would I write my own? Okay, so kind of going through that exercise.
So you mentioned reactive programming briefly.
Yeah.
So have you or anyone in this room experience with reactive extensions, particularly in C++? That's something came out of Microsoft, and that's been in Java and Scala world has been catching up quite a bit.
Right.
I wonder if anyone here has any comments about C++ version of it.
So I've used something based off of it in Lua, but not it. My biggest issue with the reactive crowd right now is I think there's a piece of work missing, which is to determine what the right set of basis operations are and what the right mental model is. Okay, so what I mean by that is the reactive guys tend to say, oh, well, here's all the different ways that you could combine values, or you could split values, or you could filter values, and they have a set of them. But I don't see people sitting down and saying, is that a complete calculus with which I can construct anything that I want out of that? Is it an efficient basis? Is it the right set of basis operations that I want? And does it map to something meaningful? Right? A lot of them, I look at the operations that they have, and I'm like, well, that's an interesting way to join things, but I don't know what it means, right? It has kind of no semantic substance to it, other than somebody being clever. So I'm hoping that kind of in the university realm, maybe in the next couple of years, some people will start publishing some good papers on reactive programming. That all said, there's a number of systems out there that are worth looking at. There's ones in JavaScript, there's the ones you mentioned. I don't know, Andre, do you have a reactive programming language you guys use? Programming.
Eric Myers, like, consulting with us, so he's like all up and down the hallway preaching.
Preaching, yeah.
Yeah, we have some stuff.
Yeah, I know Netscape, because I've seen some talks from them, are big in reactive programming, but they're also kind of a Java house. So it's reactive libraries through Java. Yes?
Are you going to have all this information in your future book, and is the code going to be available as open source?
Yes. So yes to both. The slides, probably in the set that they are, I'll ping John and I'll post them somewhere. I will post certainly the complete set of code for the tasking system. I will probably post where my futures are at right now, although they're pretty ugly. I'm not happy with them yet. That's not why I didn't put them in the slide, it's just time constraints why I didn't put them in the slides. But I'll post those too so people can kind of get a feel for how it comes together. And I've got an implementation of Win on all of them. So I've got everything I talked about here. The property model stuff at the very end of the talk, not in the asynchronous version, but the synchronous version of it is a library called Atom Libraries, which is part of the Adobe Source Libraries. And you can Google it online, and you can find, I gave like a tech talk on this topic way back in probably 2007 at Google on property models, so that's floating around out there. I continue to do work on them with Jaco Yarbe, who's the guy who did Lambdas for C++. He's doing part of the Lambda books for C++ at Texas A&M. He's got 2 National Science Foundation grants right now to work on property models. So he and I have been pushing it forward. We've got several papers out there, several more in the queue to be written. So if you know a grad student who wants something to go look at, send them my way. Because if you got a grad student who doesn't know what to do, boy, I've got lots to do. So.
Well, thank you very much.
Yeah.
So we will try to get the video up, and if you follow the meetup, we'll announce on the meetup where the video is going to be. I don't know exactly how we're going to do that yet. And if you have slides, we'll announce where that is as well. And also, we now going to meet over at Tide House, for those of you who want to join us for something to eat and or drink.